under a common design or a creation model, you can say, like, we expect similarities based on function, based on morphology, whatever you want, just because the creator, the designer, whoever, right, made things that way at the beginning of the process, right? That's totally, yes, that is a legitimate hypothesis, and we can test that hypothesis. The way we test that is by looking at sequences that mutate without purifying selection, because those sequences shouldn't maintain that nested pattern over time, because mutations are going to happen. Whereas sequences that are functional, that are limited, that are constrained, those are going to, maintain that pattern. So, like, you talk about a specific gene, right? Like opsins in the eyes is a good example, where all eyes have opsins, and you make a nested hierarchy with eye opsins, and it basically follows the morphology for like worms and vertebrates and arthropods and mollusks, right? It basically follows the pattern you'd expect. But if you do the same thing for those same groups of organisms for regions that are not constrained, like introns in those same opsin genes, the introns specifically, then you don't get that. Then you under the creation model, you shouldn't get that pattern, because those regions are just, they started separate. Even if they started identical, the way they would change since creation is going to be unrelated to each other, right? Because they are in actuality separate lineages without common ancestry. So they're going to be uncorrelated with each other. But in reality, we still find the same nested hierarchy. So yes, that is a legitimate hypothesis. We can test that, and the predictions that flow from it are not met.
So you're essentially saying those areas of the genome, the non-constrained areas of the genome, they, from the creationist perspective, they're being hit with mutations over the course of the last 4,500 years. And so we shouldn't find any hierarchical patterns if creation is true.
Correct.
Okay.
Across, okay. I want to be clear, across created kinds. So like within the dogs, for example, you would still find a hierarchical pattern because all the dogs in the creation model are related to each other, right? But if you were to compare dogs to cats, you shouldn't get two neat clades, because in the creation model, they're unrelated to each other. Does that make sense?
Yes.
Okay. So I just got one quick question for Dr. Dan there. So according to evolution, the Dalmatia evolved from the gray wolf. So can you provide to us one transitional specimen that existed between the gray wolf and the Dalmatia that existed?
I just want to be clear. So I want to make sure I understand you properly. Your contention is that dogs are not descended from wolves?
Well, I'm not an evolutionist, so no.
Okay. If you want to argue that, I'm not going to argue against you. If you want to do the species fixity thing, that's fine.
Can we just get a confirmation that Dr. Dan did not give me the name of a transitional specimen that existed? I don't know why he didn't do it.
It would just look like a dog. What do you mean?
It would look like a dog. Like it's a dog. Maybe like more like a German Shepherd than a Dalmatian. I don't
need your fantasy. I need a real
Bubbles. Which domestic dogs do you believe are related?
None of them.
Any of them?
None.
None? Like
None.
Chihuahuas.
For example, if we do a hierarchy,
I'm calling a Poe's law on this one. I'm throwing the flag. There's a Poe's law. There's no way this is real.
If we do a hierarchy based on genetics, the closest thing genetically to a wolf would be a Shih Tzu. So is Dr. Dan going to say
it's pronounced that Shih Tzu?
My bad. Anyways, is Dr. Dan going to say, since the Shih Tzu is most closely related to the gray wolf, did a gray wolf give direct birth to a Shih Tzu?
Okay, appreciate it, Bubbles.
I just want to say that that's not even true. Like, Alaska Malamutes are much more closely related to wolves than Shih Tzus. He doesn't even have his basic facts straight on literally anything he's brought up.
I just want to correct Grayson. Yes, the Shih Tzu is most genetically closest to the gray wolf.
Note that down, Grayson. When we get around to you, feel free to respond.
I'm not responding to him anymore. I think we should move past him in this conversation.
Or note it down and then put a big X through it. Not responding.
I would like to respond to the topic of non-conserved sequences and
Yeah, that's the
hierarchies
topic.
within them.
Yeah, jump in. This is a panel on this specific topic. So, T-Rock, over to you, my good man. Floor is yours.
Thank you. I was going to clarify the whole thing. I'll be honest with you. There's kind of two parts to this. On the one hand, I'm not surprised. On the other hand, it's like totally dumbfounded that that educated evolutionists with degrees don't try to connect the dots between the food source and animal genetics. It just blows my mind that they don't even care about it most of the time. It's biochemistry. You have to have something in common. Your genome as a human being, as an animal, doesn't matter whether you're a horse or a fly, like I said before, you have to have something in common with your food source. There's a reason we don't eat cyanide and paint chips, because they're not chemically compatible with our genomes. So if me and I'll use the chimp example since you were kind of comparing chromosomes to great apes and humans earlier. If me and a chimp are both able to eat a banana, that banana does essentially the same thing for both of us. It aids in growth, it aids in metabolism, it provides energy, it provides a mechanism for cellular repair. It does a whole lot of things. The fact that you guys ignore the biochemistry in the food source completely and just go straight to similarities tells me that your arguments are extremely weak, that you don't even put that much thought into it.
Can they show us constructive mutations? No. Can they show us beneficial? Well, beneficial is subjective. I didn't think even I can make a story around HIV or Alzheimer's and say it's beneficial, but constructive mutations, this is something they can't show.
Grayson, over to you.
Yeah, so it's an example of a beneficial constructive mutation, because if an organism has it, that mutation increases the functionality in a way that is the functionality of this biochemical network in a way that is beneficial to its ability to propagate its genome in its current environment. All right. So there's like when he said that if it's beneficial or harmful only relates to the individual. No, it relates to the individual in its current environment. Right. So if the environment changes, what it means to be like beneficial also changes. I mean, that should make intuitive sense to everyone. It's a very simple concept to understand. And if you don't like that example, we can always go with another example. One of my favorite examples of a beneficial, or if, Darth wants to call them constructive mutations, we can go with that, is nyelinase, which is like an entirely new family of proteins, as obviously beneficial, doesn't do any harm. It's a gene duplication and mutation, so you still have the original genes present, so that you're not reducing any functionality there. You're just getting something new that gives you a new ability that you didn't have before, namely to digest nylon. So there's another example. But on this topic of, because I've been wanting to get in on this since T-Rock initially had his statement, I wanted to go after T-Rock, was basically what I feel like all the creationists have been missing about Dan's argument is the very first point that he couldn't get y'all to agree about, which is the existence of non-constrained sequences. You have to start with that. I mean, the reason why, all of you, I feel like, have been avoiding that question, because if you accept that, Dr. Dan's argument flows very easily through a chain of logic. So it seems like you're getting hung up on that, but you're not wanting to address whether or not unconstrained sequences exist, like T-Rock bringing up that, oh, well, we would expect that if organisms are all eating the same kind of food on a biochemical level, then we would expect there to be similarities in their genomes. But inherent in that, for him to be able to make that reply, the inherent assumption in that is that these unconstrained regions that Dan is talking about are somehow important for your functionality of being able to metabolize or eat your food that you eat, which we don't have evidence for. These are unconstrained sequences. Even if they do have function, you want to say the genome's 100% functional. Even if it's 100% functional, if there are unconstrained sequences, that means that their function is not tied to their sequence. And as long as you accept that unconstrained sequences do in fact exist, and there's plenty of evidence for that, then his argument follows logically. So you have to address, like, I want to hear you guys, when you respond, say, yes, I think unconstrained sequences exist, or no, I don't think they exist, and explain why.
No,
okay,
because
no, guys, I'm moderating, please, Bubbles. I don't want people just jumping in the second someone stops. Grayson, thank you for your points. What I want to do is go someone on the evolution side, someone on the creation side, evolution side, creation side. That'll keep it balanced. What we're going to do is now hand it back to Matt. It was going to go T-Rock and then Matt. Grayson's involved. So Matt, we're going to get your thoughts and points. I have some points I want to make too. And so we'll go Matt, then Dan, then we'll go myself. And then from there, Bubbles will get you involved too. Don't worry. Jackson, it'd be nice if you can get involved as well, because then it'll make it easy to keep it, you know, creationist, evolutionist, creation, evolution. Actually, you know what, Jackson? Get out a notepad, get out a pen. You're getting in on this. So we're going to go Matt, then Dan, then me, then Jackson, then Bubbles, and then Grayson. Boom. Perfection. So Matt, go ahead, brother. You're next.
Well, since introns work with transcription, we're saying that these are functional. So if they're functional, they should form some type of nested hierarchical pattern, similar to they would in any other coding region or non-coding region. So if you're looking for regulation of transcriptions for mRNA, that leads to protein synthesis, whether or not they control some genes that are involved in regulatory or weak transcriptions, kind of like in endogenous retroviruses. A lot of them are small, so they only do transcription. But if we were to build a nested hierarchical pattern, I'm sure we would find one, because we are looking at them functionally. That would be my go-to. And then I'm sure Donnie, he's the one when it comes to endogenous retroviruses, so he'll probably have a lot better answer than me on that one. Okay, I was the creationist, so Jackson Rowe. I don't know. How about Jackson? Haven't heard from you in a while.
Donnie, step away. I need to share my screen.
Okay, share away. I'll see if oh wait, I'm not in the stream to do that. Hold on, let me.
Yeah, someone else can go until then.
Okay, all right. You want to share? Darth, where do you fall in this?
Who's looking to share?
Jackson Rowe.
So yeah, mine's kind
of. Are we
of
going Jackson next or Dan?
I just went Jackson Rowe because I hadn't heard him say anything in a while. That was all.
Okay.
But Dan, if he wants to go,
No, go Jackson. I've said a lot. Go with Jackson.
Okay, well, to be honest, I'm not feeling so good, so I kind of missed a lot of what you said there. But I do want to present something that was relevant a second ago anyway.
Okay.
So,
Sure, if you wanted to share a screen, go ahead.
Yeah, let me select it. Hang on. Okay. Okay, this is just a list of beneficial mutations I found, just reading through Google Scholar. Some of them don't say whether they increase information, whatever that means necessarily. But some of them, like glyphosate resistance, duplication mutation, glyphosate resistance in this, duplication mutation, herbicide resistance and crabgrass duplication, that herbicide resistance in, pesticide resistance in African mosquitoes, duplication, resistance in Peruvian mosquitoes, duplication, herbicide resistance in water hemp was a chromosome and gene duplication, which is sometimes bad in humans, but is not always bad. I made a bunch more, but anyway, that's pretty much all I wanted to say on beneficial mutations. I know most of you weren't arguing there weren't beneficial mutations, but some of them are clearly adding, in quote, information.
Right. I've pointed out many times that beneficial mutations, none of us are arguing against their existence. They're almost exclusively identified by their phenotype, right? The physical characteristics, with only minor regard to their genotype or genetic system. So that's why I appreciated the back and forth with Dan on the lactose tolerance, because I think the best way to engage that topic of beneficial mutations is examining the details of the genotype. What's going on? Is it reductive? Is it functionally compromising? Is it epigenetic? Are there no deleterious effects, like Dan was saying with the lactose mutation? So it's a matter of just taking the time and really going through each example. But anyways, on the hierarchies argument and the with the unconstrained sequences, the question I would have And so whatever evolutionist wants to go after me, I'd appreciate if you'd answer it. I'm kind of curious, according to the evolutionary model, if you have millions and millions of years for unconstrained regions within the genome to basically accumulate all of these mutations, why wouldn't they erase these genetic signatures of these nested hierarchical patterns in those regions? Why do they exist at all if deep time evolution was true? And I'll just ask the one question so we can kind of go one topic at a time. So whoever wants to tackle that one next, go ahead.
Sure, I'll take that one. It's because substitution rates are slow. So when you have a big genome with lots of real estate for mutations to occur, and you have a relatively slow rate of accumulation, you're able to generate, you're able to determine patterns of similarity over long distances in time without running into a saturation problem. So like, for example, you can look at regions that mutate, or I should say that accumulate mutations very quickly, right? You can look, for example, at the control region of the mitochondrial genome, and you can compare that across apes or primates or mammals or vertebrates. It gets difficult to use that as a basis across like prokaryotes and, well, obviously not prokaryotes don't have it, but like across, actually, if you look at the proteobacterial genome, they kind of do. Across large distances, it's difficult to use a rapidly mutating region like that. But you can use constrained regions that accumulate substitutions much more slowly across those vast distances. So you can compare prokaryotes and eukaryotes using the ribosomal DNA sequences, because those are very tightly constrained and have a much lower substitution rate. So it's true that some regions of the genome, particularly the unconstrained ones, are going to accumulate differences very fast. Those regions are not going to be useful across like animals versus plants versus rhizarians, right? Because there are two different from each other. You have to use slower evolving regions to make those large scale comparisons.
So you're arguing from the substitution rate within unconstrained sequences. You're saying that the substitution rate is very slow, and so major changes don't accumulate quickly, as compared to your per generation rate in unconstrained sequences that are fast.
Other way around. It's specifically in highly constrained regions where you're going to have strong purifying selection that you're going to see the slowest substitution rate. So like your ribosomal sequences are like consistent across all of eukaryotes, right? So like
it's detrimental to the health of an organism, right? Basically.
Right. So like you can't compare like human and chimp ribosomal DNA and get a nice neat pattern, because they've been apart for such a little amount of time, relatively speaking. They're basically identical to each other. You have to pick a faster evolving region to resolve that relationship. But you can compare prokaryotes and eukaryotes and resolve the relationship using at those very slow evolving regions. So it's different parts of the genome accumulate substitutions at different rates, and some parts are going to be informative across short time scales. Some parts are going to be informative across long time scales. And you just have to kind of know which parts to compare, because if you compare the fast evolving parts over long times or the slow evolving parts over short times, you're not going to get informative comparisons. It's just going to be a mush.
That sounds like special pleading, though.
Okay, go ahead.
I was going to say, that sounds like special pleading. But even if I grant you this, just because they have high mutation rates doesn't mean these mutations are constructive. I mean, they're random, correct?
That's a separate thing. I like to use the word probabilistic rather than random, because random makes people think that they're all equally likely, which is not the case. Certain types of mutations are more likely than others, and certain regions experience mutations faster than others. So it's not the case that every mutation is equally likely. But mutations are probabilistic rather than deterministic.
BRB.
Now, for sake of argument, if mutations were more so deterministic than probabilistic, what would that mean for your argument, Dr. Dan?
So then if you think back, like, however, an hour and 2 hours, whatever it was, if you think back when I showed you that table with the different predictions, then it would all be the same. If mutations were deterministic, then that goes away. Now, there have been a lot of studies on this trying to determine if mutations are probabilistic or deterministic. We've known since the 1940s, the famous fluctuation test, the Luria-Delbruck fluctuation test, that they are probabilistic, not deterministic. There have been a couple of papers recently that there were a lot of headlines saying that, no, that's wrong. And those papers turned out to not be very good. What they showed was something that we know, which is that certain regions of the genome often mutate faster than others, and some organisms can modulate the rate of mutations in a region-specific way. So they can cause a specific region of their genome to mutate faster. But the mutations that happen are still probabilistic. They can't make specific mutations occur. They can just increase the rate in parts of their genome.
Okay. I do have a couple points I want to make. I'm going to save them for a second. Throw it back to Matt. Matt, go ahead. What are your thoughts on that? Anything that's been said, let's say in the last few minutes?
Sure. If you guys like numbers, so this one will be fun. If we go for selection, how strong is it? Well, we have to look into a really conserved region. My favorite is the CO1 gene, which is highly constrained. If we look in humans, we find anywhere between 0 mutations and 10, with lots of them having very few. Now, if we put evolution to the test using their dates, and we look at chimpanzees, our closest relative, we get about 65 mutations on average in them in the CO1 gene, and that's over 200,000 years. Now, you go back 7 million years or 14 million years. We'll just go with the lowest number on this one. So now we have mutations accumulating and going to every single bottleneck. Why this matters is because over 200,000 years to get to 7 million years, you have to multiply that times 35. That's when you get to the split. So if we have 65 mutations on average looking at chimpanzees, and then we multiply that times 35, we should find 2,275 random mutations in a small CO1 gene region of just 650 base pairs. But yet we don't see that at all. We're very genetically similar in that region. So what's going on? Why would selection be removing them if we're seeing diversity increase constantly? Selection would be removing diversity, but yet we see genetic diversity.
And that's what's happening. Right. It's so you started that by saying that this is a highly conserved region of the genome, which means it's highly constrained. It's under purifying selection. So it's an important thing that we need to function correctly. So if you mess with it too much, it's not going to work. So you're going to have strong selection against changing it too much. So if every mutation that occurred persisted, then you would see, 65,000, however many differences it would be. But most of those mutations are going to cause a problem because it's a highly constrained region that's really important for physiology. So natural selection selects out, which is to say the individuals that have those mutations either don't have as many kids or maybe they die, right? So most of those mutations that have occurred historically in that gene since the split between the human chimp common ancestor, most of those mutations don't still exist in living populations. Only the mutations that were tolerable to the function of that gene still exist. That's why you see that discrepancy between the linear rate, if you just projected the mutation rate backwards, and the substitution rate, the accumulation rate that we actually see. That explains the discrepancy.
I want to make a point. I've been taking notes, and I think I get what your previous argument was on the substitution rate. I feel like it was a little vague and convoluted, but maybe you can clear a few things up, because if it's unconstrained, like we're dealing with here, it's then substituting through drift randomly. And so should scramble or basically just mutate those regions randomly, erasing this hierarchy signature that we find. And so I'm still curious why we find a hierarchy at all in these unconstrained regions if deep time evolution were true, Dan.
Well, so I just want to make sure I didn't misunderstand Matt. Matt, the region you were talking about was highly constrained, right? It's a gene that's important, right?
Yeah, that's a respiratory.
Okay, cool. Correct. Right.
But
okay.
Yeah, exactly.
So to Donnie's question, I keep doing the thing where I'm pointing the wrong way because of the so to Donnie's question, it's opposite my room versus the screen. is the reason is I think a good way to answer this is to think about the kind of weirdness with RNA viruses, right? I think you're familiar with the idea that RNA viruses, we can't resolve relationships further in the past than like 50,000 years. And the reason for that isn't because RNA viruses didn't exist longer than that in the past. It's because they have small genomes and they mutate really fast. So it doesn't take very long to bump into a saturation problem, right? Where two sites that are the same, you cannot distinguish between similarity due to common ancestry versus similarity due to convergence due to mutation, right? That's the saturation problem. With animal genomes and eukaryotic genomes generally, we have very large genomes compared to viruses and prokaryotes, and we have genomes that have low per base per replication mutation rates on average. So it would be way far in the past, so far that we don't have to worry about it before we run up against this saturation problem. And that's the reason we're able to resolve it across these large time differences, billions of years in some cases, despite the number of differences that have accumulated. And again, it's region specific. There are some regions where you do have that problem, right? You can't use the control region of the mitochondrial DNA to compare across eukaryotic kingdoms, because they're just too different. But you can use that region to compare across animal species.
But I still don't understand how substitutions won't just scramble the hierarchy signature, since, correct me if I'm wrong, those fixations are going to be due to random genetic drift, essentially, no?
Some of them will be, but in the highly constrained regions, they won't be, right? In the highly constrained regions that have...
But we're talking about the unconstrained regions and why they...
Okay, yeah. In the unconstrained regions, it's still, most of what we're talking about is going to be in the nuclear genome. So you experience a relatively low rate of per base, per replication mutations, and we have effective error checking, and you still have to contend with genetic drift, and you have to contend with the loss of diversity due to selection on linked genotypes. So you still have a bunch of things that are weeding out those mutations. They're going to accumulate faster than in the highly constrained regions, but we still don't expect them to accumulate at the per base mutation rate generation after generation, as we would expect if it was operating purely under drift because of linkage and other factors.
See, this doesn't seem consistent with your worldview. Because if you're talking about
this thing, it's complicated, right? Like biological systems are complicated and there's nuance. So yeah.
Even complication should be compatible with your worldview. But you're talking about these highly constrained regions. And you're saying if we change them too much, well, they won't work. You literally said that, like, about
are you saying there's now? Are you still saying there's now significant selection,
Donnie?
In those unconstrained regions, Dan? Well, so that's the point. Is they should be drifting fixation randomly.
I want to be clear though. You can have a slower substitution rate in a region that itself is not under purifying selection. You can still have a slower than mutation rate, substitution rate in that region due to selection operating on linked regions. You follow?
Well, I follow, but
zones are a thing, right? So if you have
population genetics says that your per generation neutral mutation rate equals your long-term fixation rate.
In haploid asexuals where you assume no linkage, yes, that is the case. But if you have linkage, if you have one gene that really matters, right, and you have a bunch of unconstrained stuff that's linked to it, you have mutations in the linked unconstrained regions. A lethal mutation in that gene doesn't just wipe out the bad mutation that was lethal. It also wipes out everything with it. Linked, right? That's what I'm saying, right? And that's still drift.
Okay, so you're saying that neutral mutations accumulate. I'd say nearly neutral mutations accumulate in linkage blocks. Okay. And basically they go unchecked. Selection doesn't see them, but eventually that linkage block can be hit with a deleterious mutation that is selectable. And so as a result, that entire linkage block is removed from the equation.
So on net, you're still going to have faster substitution rates in the unconstrained regions, but it's still not going to be equivalent to the per base per replication mutation rate. It's still
Aren't you assuming that enough of those kinds of deleterious mutations in these linkage blocks that have accumulated these nearly neutral mutations have to take place over the millions of years to basically answer this question of why these unconstrained sequences are not just scrambled to nothingness.
And this is not consistent with his worldview.
I want to be clear. Sorry, can I?
We'll let Dan go and then you go next, Bubblegum.
So we can, these are totally good and legitimate questions. It's just that like we can measure the rate and we can do the math and see like if it was accumulating at this rate, here's the degree of divergence we should see. And then we could also account for things like linkage and selection on linked genotypes. Or like we can, it's complicated, but there is math we can do to do this. And when we do that, it basically works the way we expect. Like, I mean, I can get out a whiteboard and we can like do math, but nobody wants to do that.
We'll save the math open mic for next week. Okay, I have a couple thoughts, but to be fair, Bubblegum, you go ahead and we'll just kind of run with it at this point since we're at 3.5 hours.
Well, see, that's highly inconsistent with his worldview. Earlier, he said these highly constrained areas cannot be mutated too much. But that's what evolution requires in the first place. He's not going to say that these highly constrained areas were the same as they were in their first, I don't know, the first cell. So that would be a requirement. And the fact that we have error correction for mutations, the very thing that's supposed to be driving evolution, it's a contradiction. Why would life have error corrections when it is the driving force behind its survival? You can answer, Dan.
I was going to say, I mean, I was going to say I have an answer. The answer is that mutation rate is a phenotype, and there's an optimal range for it that's context specific. Sometimes you want a higher mutation rate, sometimes you want a lower mutation rate. Like, that's what it is. It's a phenotype that's context specific. You can demonstrate this in lots of different things.
Who decides that?
The environment, natural selection. You have a curve of phenotypes for that trait. Well, don't interrupt me. You ask a question, then let me answer it. If within a population, you're going to have a curve of mutation rates, and based on that level of mutation rates, some individuals are going to be more likely to survive and reproduce than others. And those individuals, if mutation rate is the salient trait in that context, then you're going to have that population shift based on selection towards the optimal mutation rate, whether it be higher or lower than the average at any given time.
Well, you're just presupposing these mutation rates were different in the past.
No, what I'm saying, like, that's actually directly observable. I've actually done that myself, where there are viruses that actually artificially elevate their mutation rate. And if you chemically mutagenize them, the mutations that they select for then bring their mutation rate back down into the range you would expect. So no, I'm not, I've directly observed the thing I just described. Sorry.
But here's the trouble. Why do we have these error correction? How do you reconcile error correction with mutations?
I just answered that.
No, you didn't. You just told me. You just like, well, I presup these mutations happen. Okay, sure, I grant you that.
All right, we do it again. Mutation rate is a phenotype, and in any given ecological context, there's going to be an optimal mutation rate. So if a higher or lower mutation rate than the current average is a salient trait for fitness in a given population, then you're going to see selection for either more strict or less strict error correction until that population gets to the optimal average mutation rate.
Sure.
And again, I have directly I've done this in the lab.
I agree with you. It'll probably, you can have mutations increase the fitness, but it will not increase its survival. So the problem are the mutations in and of themselves. Why does life have error correction? It shouldn't have error correction if your mutations are required.
Bubblegum, why are you assuming that it wouldn't? If you're saying that it would benefit their fitness but not their survival, why are you assuming that?
That's why I'm asking you. Why are you assuming that?
It doesn't track.
So, that doesn't logically follow. Why would it not be good for their survival to increase their fitness?
Just because something could be increase their fitness does not mean it increases their survival.
Yeah, explain that. Why not?
For example, I can give you an example. Let's say you're a person with AIDS, and you can attract a person who is a bug catcher. Sure, that'll increase your fitness, but that is not the survival of that population.
What? I don't even know what you're talking about.
I'm talking about fitness versus survival.
Yeah, I don't understand.
So when I'm talking about survival, I'm talking in the terms of population.
Why are you talking in terms of population instead of talking
because
about
the
fitness? You're saying that
I talk in terms of population because evolution happens in terms of population.
Yeah, so you're saying that what can increase the fitness of a population isn't good for the survival of the population?
I'm saying what can increase the fitness does not necessarily mean it'll increase the survival.
So yeah, provide an example for that, but don't use confusing terminology about bucks or something. I didn't understand what that meant.
For example, you can have let's say you have a little tribe of bug catchers. You know what a bug catcher is?
Like bug?
A bug catcher.
No, I don't know what you're talking about.
It's somebody
that catches insects.
No, it's a sexual term for people who are attracted to people with STDs.
Oh, okay.
So that can be a
benefit. I have no idea
benefit.
what you're talking about, man.
Donnie, can we seriously? This is pointless.
I'm talking about what is fitness.
Can you pick a less weird example, please?
You are talking fitness in your definition.
I've never heard this term in my life.
Yeah,
we don't need to do this.
Just
if
what you're saying is true, then just come up with a different example of it, please.
Guys, I want to get back to the topic with Bubbles. I appreciate I gave you a chance to respond.
I am on topic. I mean, they're just denying fitness. Fitness just means the ability to reproduce.
Right? No, I'm not saying you're completely off topic, but in terms of the unconstrained regions and basically the question,
I'm asking. They can't say that these constrained regions cannot be mutated past a certain level because that's contradictory to their whole worldview.
No, there are constrained sequences and there are unconstrained sequences. Nothing about that is contradictory.
You're going to have to say these constrained sequences didn't exist.
Well, I'm just curious because Dan. So, are you saying that when it comes to basically your per generation neutral mutation rate equaling a long-term substitution or fixation rate, you were saying that doesn't apply to diploid organisms?
You have to control for a bunch of other factors is the way I would say it. So you can model it very readily in haploid asexual populations. So like this is why Jensen, for example, loves to do this for the Y chromosome and the mitochondrial DNA, because you can approximate haploid asexual populations for those two parts of the genome because they are largely but not entirely non-recombining, right? Once you put diploidy recombination, it gets more complicated.
Well, I appreciate that, but I guess my question is, here's the article that Chris Roop and I wrote, and we have this quote from evolutionary biologist Douglas Futuyma, however you say that. Futuyma. Don't
make the Jensen error. Know how to pronounce his name.
Futuyma. Say it. Okay, I'll never mess it up again. So, yeah. So he says, I guess if you can speak to this a little bit, is he agreeing with you? I mean, he's saying it would take 4 NE generations for such mutations to reach fixation. About the same number of neutral mutations should be fixed every generation. Mm-hmm. The rate of fixation mutations is theoretically constant and equals the neutral mutation rate. So the way I interpret that is your neutral mutation rate today, what we observe, will equal over time the fixation rate. Can you speak to that, Dan?
This is this is the from the introductory level evolutionary textbook on this topic. When you do it for real, the math is more complicated, and that last sentence is the key there. This is the theoretical basis of the molecular clock. That is true. That is this is like the Hardy-Weinberg version of a molecular clock, right? If you know what that means, right? It's the idealized case that you don't actually find in nature. When you do this for real, it gets more complicated because there are confounding factors at play.
Okay, so you're saying this is the theoretical basis of the molecular clock. So in theory, your neutral mutation rate will equal the long-term substitution or fixation rate.
If you could isolate a sequence from all other sequences and that sequence strictly operates under genetic drift and there's no recombination, there's no inbreeding or whatever, right? It operates as a haploid. If you could You know, if you're familiar with the phrase "a spherical chicken in a vacuum," right? That's what we're talking about here.
So so you're saying the math is complicated, the math contradicts what the theoretical basis of the molecular clock is?
It's just more complicated. The
complicated.
theoretical model approximate it.
It's multi-dimensional. So have you done the math? You said that you'd pull out your whiteboard, but, you know, maybe that was tongue in cheek, but like, have you done the math to see if it's complicated enough to be different to what he's saying?
In what organism? In what organism do you want to talk about? Because for some subset of organisms, the answer is yes, I have done the math.
Well, if we're talking about human beings,
then no, I haven't done the math specifically for humans.
Well, and that's the problem I have, is because we oftentimes discuss mitochondrial Eve, Y chromosome atom. We talk about genetic entropy, and usually we're discussing humans. And so if the neutral mutation rate, the per generation neutral mutation rate equals the long-term fixation rate, but you haven't done the math.
Oh, no, I haven't personally. Humanity has done the math.
Okay, so it has been done. You're saying?
I have not. I thought you were asking what have I personally done the math on.
Right.
And no, I've done this for like viral phylogenetics. So I have not personally done this type of thing for human time to most recent common ancestor stuff, which is a little bit to the side of the topic we were talking about with the constrained versus unconstrained sequences. But it's I
think it goes back to the challenge I posed or advanced, that your unconstrained sequences, basically these mutations should be randomly drifting to fixation. And so
approximately
we should find those unconstrained sequences mutated to the point where there is no consistent signature or hierarchy, but we do find a hierarchy. And I find that to be curious if deep time evolution is true. So maybe it's going to depend on what organisms we're looking at, but pick your non-haploid asexual organism and let's run the math, basically.
That's fine. I mean, that's fine. I just want to be clear, though. You agree with me that we do find the nested hierarchical pattern in the sequences we're talking about, things like herbs and stuff. We agree on that, right? We find that pattern.
I agree. Yes.
Okay, great. So that is an explicit prediction of evolutionary theory.
No, but I'm showing I don't think it is a prediction, because the reason we find that. but the question, why do we find a consistent hierarchy in those unconstrained sequences?
Because
if there's no selection or there's limited selection, mutation rate is higher in unconstrained sequences. And so over millions of years, those mutations should alter those sequences to the point where we don't find a consistent hierarchy.
I mean, that's just empirically not true, though, right? We can actually do that.
Yeah, Donnie, think about the numbers here between like the size of a genome, which is like, you know, or the size of the total unconstrained regions in the genome. Like that would be the bottom half of your fraction there. And then think about how many neutral mutations are going towards fixation per generation, times however many generations you're talking about and the length of time that you were talking about. And just what does that fraction look like? Because you're trying to say that the numerator should be much larger than the denominator. But like think about the math involved here with the actual numbers. I think the denominator is probably going to be bigger.
Well, it sounds, again, a lot of points being made that I think need to be tested. Dan, has said that the math has been done in some creatures, but it's something that I'll reflect on. But I still don't feel like that question has been adequately answered as to why there is a consistent hierarchy in the first place if deep time evolution is true. I understand what you're saying, Grayson, there. I understand what you're saying, so Dan, as well. But go ahead.
I have if it's okay with you, I have a question about something else, but I just want to wrap this up. If we want to talk about something else, great.
Okay, let's wrap up this topic. You can have the last word if you want. Go ahead. You brought it up.
It took a while to get to here, right? But we kind of got to. We agree that there are nested hierarchies in unconstrained sequences. We disagree that is a prediction of universal common ancestry. I think it self-evidently is the case that is a prediction of universal common ancestry, that you'd have these nested hierarchies. And final point is just, is that a prediction of separate creation? And the answer is no. Explicitly, it's the opposite. So the key thing that I was trying to convey all those hours ago to Kent was that the pattern that we see in these sequences, the hierarchical relationships across created kinds, right? That's a direct refutation of a prediction of separate ancestry. And there's a reason I clarified before that the separate ancestry model that Brian was talking about, that I think everybody kind of buys into, is that there's no divine tinkering as it goes on, or it's a one-time deal. And if you have that one-time creation with no tinkering, then the pattern that we observe is an explicit falsification of that hypothesis. That's the key here. I don't think I'm going to convince anybody of that, but
well, that's quite a negative.
I'm happy we're able to get to that point.
Just because you can draw up a pattern doesn't mean one came from the other. Again,
it's like I said, I wasn't going to convince anybody.
Again, Dr. Dan, you're just presupping the transitionals. You can't even
agree that for humans that does mean exactly that. Like if you have
not even for humans.
If you have two humans on Earth, you compare their genetic sequence homology, you can tell how related they are.
You can draw a pattern on anything, but the fact of the matter is the genetics does not match your little pattern hypothesis.
Okay, do you believe in paternity tests?
Yes.
So then you accept that the genetic sequence similarities between two individuals can in fact be used to determine ancestry.
For things that are you can actually do. For example, a mother and a son. Yes, you can do that. Because that doesn't require a precept of evolution.
Well, it requires that you acknowledge that genetic similarity does, in fact, indicate relationship.
Just because they're similar, just because you see a pattern, doesn't follow.
But you just said it does follow for like a mother and son or siblings.
Because that's a logical necessity.
Yes, and exactly what we're talking about is a logical necessity given the genetic similarities between non-constrained regions in different species.
Do you think evolution is a logical necessity?
Given our evidence, yes.
The evidence is patterns. You don't have any genetic evidence. You do not.
The patterns in genetic sequence similarities, just like it makes it a logical necessity in a paternity test, also makes evolution a logical necessity, at least shared common ancestry.
Grayson, you have zero genetic evidence.
That is objectively not true. We have
objective. You sure about that, Grayson?
For lots of
you sure about that, Grayson?
Yes.
Grayson, provide to me the transitional between the gray wolf and the Dalmatian.
We can just.
You don't have genetic evidence.
Here's exactly the answer. Okay. Sequence the wolf genome, sequence a dog genome, and you can tell based on their shared sequence similarities
that
they share a common ancestor in the exact same, using the exact same set of logic. Wait, let me finish this. Using the exact same logic as a paternity test.
That's an assumption there, Grayson.
What is real? Okay with it, Grayson, for the human paternity test.
Grayson, what's real genetic evidence? It's you finding that transitional and then taking its DNA and then testing it.
That is not the only criteria that can show us emphatically, empirically, that evolution happened and shared common ancestry is in fact existent.
Grayson,
because
you think
what would be a sufficient criteria of showing that would be the genomic sequence similarities between a wolf and a modern dog.
Grayson, do you think DNA is only part of the evolution model?
I don't know what you're asking about with that.
Do you think DNA is only part of the evolution model, or do you also think?
Okay, I will answer that, but not the existence of DNA, but the patterns of genetic similarity forming nested hierarchies. Yes, that is only part of the evolution model.
Wait, so you, according to you, if God created a Dalmatian and I don't know, let's say a pit bull, those genetic sequences should be entirely different. So you think, according to us, we should be able to code a dog. God should be able to code a dog via the same genetics as a dinosaur. Is that what you're saying, Grayson?
I don't understand what you think I'm saying with that.
So you're saying
repeat it in a way that makes a little bit more sense.
So you're saying we should So Grayson is saying we should not find these patterns in the DNA.
Yes, specifically the unconstrained sequences.
I'm going to jump in, guys, because Dr. Dan said he had a question before he's going to get out of here for, if I remember correctly, Matt and myself. And Matt is back. I just confirmed Matt is back. So, Dan, to be fair, if you did have a question.
Just finish.
Yeah, this is a little bit behind, pulling back the curtain on the nuts and bolts of all this stuff a little bit. But my question is this. We've been sitting here chatting about this stuff with constrained and unconstrained sequences. And we've had, I think, a really good conversation about it. We're really digging into the weeds, and it's been an excellent conversation, getting into some really technical nitty gritty here. My question is this. This type of conversation is not possible with Kent because he doesn't know anything. He doesn't understand any of what's being talked about here. Why do you still give him the time of day? Like, he doesn't know any of this stuff. Last time I was here, he said the thing about the recombination is mom's unzips and dad's unzips and they wind up together. And like, Donnie, you know that's nonsense. You know that that's not how that works, right? Like, why do you still waste the first hour on that, and then however long in the open mic with him there? It just makes it impossible to have any kind of conversation because he doesn't know anything.
I can answer that question for you. Same reason modern day debate invites flat earthers and Christians to make fun of them.
Well, let's be nice to people who aren't here. I think we all have our specialties. I think we all have the areas that we focus on and understand the best. Matt and I, for example, we like to study the genetics topic because, Dan, as I think you would agree, the best possible evidence for common descent is in the world of genetics. I really believe that. And so that's the topic I like to focus on the most. And so we enjoy a good debate, and Kent's specialty may not be in the world of genetics, but I think he's got his own set of specialties, and I think he's a good debater, makes for a fun debate, entertaining debate. We like to get people in the ring, so Matt, what's your answer? And then Dan, sure, you can respond.
I think Dan triggers him too, because he said he's just reading a script again,
which is true. Tell me I'm wrong. Then he gets mad. Tell me I'm wrong.
Then he's mad. So then he's not even listening to your question.
Well, Dan and Kent, they got a love-hate relationship, so they're good at triggering each other.
No, I mean that was a good example though, right? Because I asked, I the way I approach this, and Donnie and everyone here knows this. The way I approach this is I start I try to establish a common foundation of just like definitions, right? Like, do we agree that this is what this means and this thing exists, right? And I couldn't even get that without him going to his stupid script on DNA complexity, right? And it was completely irrelevant. It was just pluck out a couple buzzwords in what I said and find the part of his script that sounded like it was related to that. It's like, it's impossible to have the kind of conversation we just had when he's present in the room. And it's like, Donnie, I see what you're trying to do with these open mics, and I will tell you, I appreciate it. And I wouldn't be here if I didn't think that this kind of conversation was valuable, right? But why do we preface it with 2 hours of that, right? That is essentially wasted time where there can be no constructive, detailed conversation like the one we're having. And I get that it's a spectacle and that's fine and all good, but even tonight, when I popped in about 30 minutes into the debate part, there were only 100 people here watching. It wasn't even like it's bringing 500 or 800 or 1,000 people to watch Kent anymore. So what's the value in wasting everyone's time letting Kent recite his script for the 100th time?
Well, I appreciate the feedback. I can speak for Matt and myself. I can't necessarily speak for Kent, but we like to dig deep into these topics. These are the topics we like to focus on. And so I enjoy going into the nitty gritty. And that's usually what we do at these open mics is after the first 2 hours. Last week we dug deep in the hominin fossil record with Gutsy Gibbon was here. Is an excellent time. Week before that, we got into some other heavy topics related to, you know, the age of the earth and so on. So I guess within the 5-hour open mics, we get a little mix of everything, you know, and then that's why me and whoever the host is, we'll make sure we stick around for 4 to 5 hours to allow anybody who wants to join and whatever topic people want to discuss. Like in this instance, Dan, I had a really good time discussing this topic is a great topic. And so I've had a lot of fun, and I'm glad that we've had the time to discuss it.
That's fair. And I'm gonna head out because I've been taking up a lot of time here, and I appreciate all the time you've been giving me. But I just want you to think about the cost benefit here. Because, you know, I could see the argument if you go back like 2 or 3 years when kind of the YouTube, especially like with the pandemic, people are spending a lot more time online. You know, the debate scene drew a lot of eyeballs, right? I don't know what your views were for an average Kent debate, but it was, you know, it was up there. It was drawing a crowd. And, you know, like I haven't been paying attention for the last few months, but I popped in just over the last couple weeks to see a couple of these. And like the numbers are not what they used to be anymore. So like, you know, I hear, you know, everyone has their strengths. Everyone has the thing that they focus on. I feel like Kent's strength is the spectacles. People are saying in the chat right now, it's drawing a crowd. But like it doesn't do that anymore. So if the goal is to draw a crowd, that's not doing it. If the goal is to have an in-depth conversation, his lack of understanding of this stuff, which I mean, people are going to say that's mean, but like, tell me I'm wrong, everybody. Tell me Kent does actually have the ability to have the conversation that we've just been having for the last couple of hours. He just objectively doesn't.
I mean,
he doesn't
I will say my last debate with Kent, he kind of went off topic. He like intentionally, it seems, wouldn't even hypothetically entertain my points. And that was kind of frustrating. About halfway through, I kind of mentally checked out, to be honest.
Well, yeah, that kind of reminds me of something, Dan, if you don't mind, before you leave, I want to be absolutely fair to you because you have been very courteous tonight. I think it's been a great discussion and another great open mic. You were in the middle of making a point here on the Y chromosome. And I'd like to give you that opportunity to maybe finish that point. We can wrap it up here. I know.
And then I'll piece it. Yeah, that's fair.
Yeah.
I appreciate it. So my point was, so you were saying that if you look at this, you could see that the chimp and human chromosomes are very different. And it's actually the gorilla is more similar to the human, right? Relative to the human and the chimp, right? If you look at that, if you do a set of pairwise comparisons, human and gorilla is the most similar. But the key thing there is that is a structural comparison, and that's what it says in that little blurb in the bottom right corner there. If you look at the sequences, because that gray bar in the left, kind of the bottom side of the human Y chromosome, it's mostly repetitive stuff.
Right here, yeah.
So it's like you can't do a useful sequence comparison on highly repetitive DNA. If you do sequences and don't worry about the repetitive structural stuff, you just go basically from like the midpoint of the chromosome up, just above that dull gray bar up. Then by sequence comparison, the question I was trying to ask, and Kent interrupted, was what's more similar in human, chimp, gorilla according to the sequence of the comparable regions? And the answer we all know is human and chimp are more similar, and then the gorilla is the odd man out there. That's when you do a sequence comparison rather than a structural comparison. That was the point.
If I could ask, okay, I appreciate that. If I could ask a clarifying question though, since, and you know, here's an excerpt from, is it the same paper? No, this is a 2021. So since they point out that the chimpanzee Y is only half the size of the human Y. So if we were to just look at sequence by sequence comparison, basically of all the base pairs, because it's already right off the bat half the size, isn't there already going to be then half the sequences just not even there to align and compare in the first place? Like, can you speak to that?
That's a great question. That's a great question. And this has to do with how you do alignments in your matrix and score your alignments, your matrix for comparisons, because it basically, how do you score like deletions, translocations, that kind of thing. And you can do it on a per nucleotide basis. So if you have 1,000 base pair deletion, that counts as 1,000 differences. But I think it's more realistic and better reflects evolutionary history in terms of like how things happen, to take those types of changes and count them as one event that occurred, right? 1,000 nucleotide deletion is not 1,000 mutations. It's one event that wiped out 1,000 nucleotides at a time.
If I could, and that's a good point, Dan, if I could just jump in just to clarify again. So if we have 1,000 base pair deletion in, say, the chimpanzees, so you have 1,000 base pair region basically that doesn't exist in the chimpanzees, but it exists in the human genome. Are you assuming that 1,000 base pair region was deleted at some point since the split, right? You got humans and chimpanzees that go back to a common ancestor. And since that split or divergence, chimpanzees experienced 1,000 base pair deletion. The humans didn't. Is that essentially what you're saying?
Yeah, I totally get the question. And the answer is not necessarily. I think because so you can do it in a way where you are basically hypothesizing an ancestral state based on some outgroup, right? So if you're saying, for example, that gorillas are the outgroup, right? And then humans and chimps are sister taxa, you might look at gorillas and say, do they have the deletion or not? If they do, you might say that the absence of that region is the ancestral state, and a duplication or something resulted in a gain of those bases in the human chromosome. If the gorillas share the longer state and the chimps are missing something, then a more reasonable hypothesis would be that the chimps experienced a deletion. So one way of doing it is to hypothesize an ancestral state and say, yes, this one has a deletion, this one doesn't. Sometimes, though, we either don't want to do that because we're not sure, or the data that we have are like genuinely ambiguous, right? And it would be inappropriate to hypothesize what the ancestral state was. So we just count it as a difference that occurred at some point in one lineage or the other without hypothesizing which one specifically.
Now,
right?
as creationists, and I appreciate this, but I'm following you as best I can. So as creationists, though, how would you argue we should approach this issue, since we wouldn't assume that humans and chimpanzees go back to a common ancestor? We also wouldn't assume that all DNA differences, as you know, are the result of mutations. And so if we look to 1,000 base pair deletion, are we considering that one difference, or are we considering it 1,000 base pairs? So 1,000 differences from our starting point.
Just mechanistically, I think it's more appropriate when you have a region that one genome has and a comparison genome that we think is the sister group doesn't have it. It's reasonable to treat that as one evolutionary event, whether it's an insertion or deletion. Sometimes we can't tell, but I think it's reasonable to treat that as one event that occurred rather than 1,000. But to answer your direct question, from a creationist point of view, you're going to run into this problem no matter what kind of group of species you're looking at, because at some point you're going to have some inconsistencies in your phylogeny. That's just a fact of life. So, like, I don't want to, stick a position on you, but let's hypothetically say that dogs, wolves, foxes, coyotes are the same created kind. Let's just hypothetically say we take that as our position. You're going to find instances like we're talking about within those species where one combination you see in insertions or deletions, different combinations, you see a different set of insertions, deletions that would lead to a different pattern of relatedness. So you run into this pattern no matter whether you accept common ancestry of humans and chimps specifically. This question of how to deal with these differences is going to come up unless you do the bubblegum thing and just say all species were independently created. Then you solve that problem. You create a million other problems, but you solve this problem that we're talking about, right?
Now, okay, and I appreciate those points. Specifically on the Y chromosome, though, I wonder if we would find this amount of dissimilarity between, let's say, the example you made, your canids, basically, foxes, coyotes, wolves, dingo, so on and so forth. I wonder if we would find the extreme dissimilarity in the Y chromosome within those species in a family that we would say belong to the same created kind.
100%. I can give you an example. Hang on a second. Just give me 1 second. I have to remember. It might take me a minute to find it, but there's deer, where it's sister taxa of deer that are
Dan, while you look for that, can I really quickly share my screen on this topic? Just
go for it.
I've got
actually before you do, Gracie, I feel like I'll forget to ask. I feel like I'll forget to ask Dan when it says here, and I know you're looking for something, so I apologize. Puzzlingly, in terms of shared genes and overall architecture, the human Y is more similar to the gorilla Y than to the chimpanzee.
That's exactly what my quote is about, Donnie. On my shared screen, it's exactly addressing that.
Dan, how much genetic?
Well, I want to ask my question. When it says shared genes, is that not also discussing your sequences, your base pairs?
Just look exactly what I shared. It answers this exactly, Donnie. It's exactly answering this.
I think I know what Grayson's going to show, and yeah, just
like literally, this person right here says what you were saying, that the gorillas have some unexpected patterns that in size. But if you compare the sequence identity, so not just the gene content, not just the structure, but the actual sequence identity, humans are more similar to chimpanzees as you would expect.
Right, and that's what we've been talking about. But I don't want to look. I want to look at everything. I want to look at the size. I want to look at the architecture. I want to look at.
But the only relevant thing is the sequence.
According to who?
Cherry picking.
According to you, you're cherry picking that because you don't like the fact that the Y chromosomes are so dissimilar when you consider everything. Now, I understand what Dan is saying is we need to ask the question, hey, is the fact that the Y chromosomes are only half the size based on some massive gene deletions, maybe since the split? And so should we actually consider that? Or if you found 1,000 base pair deletion, are we going to say that's 1,000 differences, base pair differences, or one? I think these are valid questions, but Dan, I see your screen shared. Go ahead.
These are sister species of deer. Yeah. They're undeniably the same created kind by any reasonable standard.
So I'm looking at the Y chromosome.
Not by my standard.
In the Chinese, to Bubbles, that's true. In the Chinese one and the Indian one, the Y chromosomes both look pretty.
The Indian one has 2 Y chromosomes. There's 2 separate Y chromosomes, Y2 and Y1. Y2 and Y1.
That's called Jacob's syndrome, right? Where you have 2 Y chromosomes. That
usually comes with
just kind of no, it's not an aneuploidy. That's just how that species works. It's not an aneuploidy.
So if they go back to a common ancestor, how did one species get a second Y chromosome?
Fusions and weirdness, like it happened. I mean, look, if you want to dispute that these 2 things share a common ancestry in a creation model, then like power to you. But you're on Bubblegum's team now.
Well, but how did that happen? How did one? Because it seems like this is an anomaly. I don't want to take an exception and overturn a rule. Like I don't want to say, well, okay, so because we have this example, which is kind of flabbergasting. That's interesting. I'd like to know how that happened if anyone has an answer. But to now apply this to the Y chromosome dissimilarity in humans, I don't. That might be apples and oranges. Dan, go ahead.
Here's the relevance. And then I am going to go because I've been here a long time. Here's why this is relevant. The question is, well, how could we get this pattern of Y chromosomes within apes? They're so different. How could we get that pattern if they are the same kind? The difference in the Y chromosome structure must mean they're different kinds, right? Well, here we have 2 species of deer that are sister species of deer, right? They have wildly different genome structures, including not just different structures of the Y chromosome, but actually different numbers of the Y chromosome. Now, by any standard, whether it's Ken Ham at the Ark Park or Kent, any young Earth standard that has created kinds that are not individual species, these 2 deer are going to be the same created kind. We all should agree on that, except Bubblegum. Given that agreement, which I hope we can all agree on, then that's it. Then we don't have to worry about, can you have that level of divergence in the Y chromosome structure within a created kind? You obviously can.
Well, the Christian can posit that there were multiple deer creations, and these 2 deer got off the ark.
But this one has an entirely just almost duplicated Y. It's like a second Y chromosome.
There's a weird, right? Isn't that cool?
Well,
it doesn't matter.
Dr. Dan,
what matters is that they're the same kind.
Dr. Dan, you should be
But
able to
how does
defend
this
evolution.
how does this deer species get a second Y chromosome? Like, how frequent is this in the biological world?
Probably not very frequent, but not zero.
Well,
this is
really not zero, but like maybe there's a very simple explanation, because it doesn't seem like anyone in the panel knows how this Indian deer just has a second Y chromosome. I mean, that's interesting.
Well, chromosome numbers vary all the time between closely related species.
Well, you guys are pre-supping evolution.
No.
Yes,
no,
you are.
I'm pre-supping creationism. I'm saying assume the created kind. Look
is that an Oh, I totally agree with you, Dr. Dan. I totally agree that the atheist evolutionists have simply stolen microevolution from the Christians and just taken that lie and ran with it. I totally agree with you there. But that's still no excuse for you not to be able to defend your own position alone without leeching off the Christians.
Okay. Donnie, so that I think is the Y chromosome thing we were talking about earlier.
Hey, let me just say this one last thing. One of
then I'll just say goodbye and then
Okay. One of your, where is it? Let's see. I know you and Dr. Rob Carter go way back. And so right here. So he puts out a challenge. And so that's what I'd be curious about, these two deer species, the Chinese one and the Indian one. Is there a simpler explanation for why one of them just has a completely duplicated Y chromosome, basically?
Well, he's going
as compared to the Y chromosomes in the great apes, including the humans. You know, Dr. Rob Carter asks basically for a sophisticated mathematical model that shows how these Y chromosomes can change in terms of wholesale rearrangement of significant parts, evolution of entire gene families, you know, in a relatively short amount of time since the split. So I wonder if there's a simple explanation for that, though. Right, because in order for us to take this seriously, is like, am I being echoed or something? I just keep hearing commentary. So my last thing to Dan, and then I'll give you the last word. I know you got to get out of here. Is, don't we require a mathematical model to go with the hypothesis for us to take it really seriously?
I mean, do you think evolutionary biologists aren't doing that?
No, I understand they are, but I don't know if they're doing it here because, because here as late as 2020, they point out that, well, you know, sperm competition might explain it, but this hypothesis still needs to be evaluated. So that's my question: is, has it been evaluated? Have they provided any math, any data on this?
I would bet, and again, this is human Y chromosome stuff is not my specialty, but I would bet that people are working on it. That would be my hypothesis, and that's a testable, falsifiable hypothesis, but I would bet that's what's going on. So I thank you for all this time. This was actually really technical and enjoyable, and I had a lot of fun doing this. You just referenced Rob Carter. Have Rob Carter on. You could have a good conversation with Rob Carter. Don't waste time. Like, why are we doing the Kent thing? Have like good people on that actually know what they're talking about. That's my takeaway, everybody. Have a good night. That was fun.
Hey, wait, before you leave, last thing I'll say, you know what would break the internet? Dr. Carter versus Dr. Cardinal.
You get him. You get him. I will come. If you get Carter, I will, and he's open to it. I will talk to Carter. I will do that. I would love to talk to Carter. So many things to talk about.
There we go. Great way to end it. Cool Jesus and Joel Duff both agree.
I would be there for that.
That was fun. Stop giving Kent time. Do interesting things instead. Later.
Okay, Dan, thank you for joining. That's 4 hours on the dot, actually. So, and Dan joined relatively right away. So 4 hours. That was a ton of fun. And so Kent and Dan, they got a love-hate relationship, hopefully more love than hate. We love Kent. We think these open mics are a ton of fun. Kent's a good debater, and we have fun hosting the debates. So, okay, that was fun. I'm glad Dan joined. And man, we talked about a lot of interesting topics. This has been a good open mic. To those in the audience, you know, I think this is our 8th or 9th so far this year. We've been doing them very frequently since the summer, every 10 days. Usually we go between 4 or 5 hours, but okay. Like, I don't know, Matt, I know you only wanted to stay for 4 hours. I got maybe a little bit more in me, but we've also got a big event tomorrow starting at 6. We got a big soteriology debate, so I don't want to be too burnt out for that. Anybody got anything they want to say? Any points they want to make?
Yeah, I want to share my screen.
I think Grayson came to repent of his Lenski errors.
Well, Grayson was making earlier an argument that like he was making the assumption that DNA is only part of the evolutionary model. Of course, he goalpost shifted that into like the pattern. Yeah, I know.
It's a very scientific chart.
It's supposed to be a dog. I can't draw a dog. Okay.
It looks like a platypus.
Yeah. So, anyways, he was let me get my marker out. So he was making the argument. It's because of the patterns that we must assume evolutionary. But he's just making the question: does he think God is not going to code a dog using non-dog DNA? Does he expect God to code a dog using, I don't know, flamingo DNA? I mean, what defines a woman, a female, if not their DNA?
Bubblegum, you understood that we were talking about in unconstrained regions, meaning regions that their function does not have to do with their sequence. Right?
I love this picture.
Their functions don't come again. Their functions
if they're
don't.
Non-constrained, then the function of that region doesn't have anything to do with the sequence of the DNA. If it's non-constrained.
Non-constrained.
Yes.
Well, you're just talking about genes shifting around.
No, I'm not. I'm not talking about genes. I'm talking about unconstrained regions. Those are not genes.
Oh, unconstrained regions. Yeah. Why would you expect God to not put unconstrained regions? You know what happens
is similarities in the sequence in these unconstrained regions between multiple different species.
Yes.
That is what is the differentiating lines of evidence between creationism and evolution.
A dog is going to have the same constrained regions as another dog.
Unconstrained
regions as another dog. Why would you not expect that?
I would argue that because your protein coding genes, right, they're basically constrained. They're your building blocks of organisms. And yet we actually find that they're a lot more similar between creatures. But your non-coding regions of the genome, a lot of your non-constrained or non-conserved regions of the genome, on the other hand, they are more organism specific because they regulate a lot of what the protein coding regions or conserved regions are functioning in. They're basically providing the metadata for the building blocks that are the protein coding genes to function.
A very small percentage of them do that.
Well, I would argue because we have evidence for somewhere between 60 to 80% genomic activity. And within that 60 to 80%, what do we find?
They don't say genomic activity in the ENCODE project. They don't say it like that. They say biochemical activity.
Right.
Which just means that any random thing is binding to it. That's background noise.
But that's where the debate is. Is the 60 to 80% biochemical activity, is this just genetic noise? Is this spurious transcription? I would disagree. That's your
But you'd have to have evidence.
That's your claim
to support that.
But you don't have evidence to support that it is spurious or that it's genetic noise.
Yes, we do.
No, you don't.
Yes, we do. We have
the
transcriptome.
The evidence we have suggests that most of that activity is functional activity. Transcribing portions of the genome.
Not the case. That is just
transcribing. Anytime you add a single nucleotide to a growing RNA chain, and Matt knows this, you're utilizing ATP. You're utilizing energy. But if you have all of these transcripts all throughout the genome, you have all of this activity, it doesn't make any sense that that would just be useless activity. Why is the genome, why is the cell utilizing energy and utilizing ATP? It would be wasteful of energy and resources. Why not just do away with it over time? Get rid of that.
Because we're not intelligently designed to be 100% efficient.
right there's
If
just a
we
whole lot
were
of nothing.
intelligently
That's not an
designed,
argument.
Donnie, then we would be 100% efficient.
The activity,
100% efficient.
the
That's
60
impossible.
listen, the
Physically.
60 to
God could do it.
70% activity.
Well, God,
The
but
most
God is
parsimonious answer is that it is functional simply because transcription is an energy intensive and resource intensive process. Okay.
he's
If
literally asking.
if this wasn't useful activity, then again, if evolution is true, since it's wasteful of energy and resources, selection or whatever evolutionary mechanism you want to point to should have weeded out this genetic baggage over time. That's a fact. That's a reality.
It's not a fact.
Requesting to defy the laws of physics.
No, I'm not.
You said you want 100% efficiency.
If God could do that, yes.
Oh my God.
There are certain systems within biology that approach 100% efficiency.
Nothing is going to be 100% efficient.
Certain things absolutely approach that limit.
It would go against the laws of physics to do that.
No, I don't think you understand physics very well, Bubblegum.
It would literally go against the laws of physics for anything to be 100% efficient.
I don't think you understand the laws of physics very well. What's the highest level of physics that you've had?
High school, and that was.
I'm
glad I dropped out of that because that was garbage.
Oh, you dropped out of high school?
No, I dropped out of that class.
You dropped out of physics in high school. Okay.
Well, first off, no. First off, they gave you like a mandatory and then an optional.
So, for example, I could go through just a number of papers on introns, ERVs, ALU sequences, all kind of non-coding DNA, like long non-coding RNA genes. And this is just a paper from 2021. And you can find over and over again them saying things like this. Evidence for their role in regulating cell immune responses or whatever function it is growing. And so as a creationist,
at a very low percentage.
Grayson, every time I say something,
functional to non-functional.
No. See, again, you keep saying, oh, but the number of functions, it's basically shrinking. It's getting smaller and smaller. It's not like the genome's getting more functional. But again, that goes back to, this is circular reasoning, Grayson, and I love you, but circular reasoning is a fallacy. Okay, we have evidence for 60 to 80% activity in the genome, biochemical activity. You're saying that's noise, but that's an argument without evidence.
It's absolutely not an argument without evidence. The
yes,
evidence,
it is. Even that statement you just made is an assertion.
The evidence is that those transcripts that we're saying are spurious activity are in such exceedingly low concentrations and are degraded so quickly that there's no conceivable way that they would have a function with that low, with that low amount made being degraded that quickly before they have a chance to have any function.
What's being degraded?
Percentage of that are you talking about?
What's being degraded, Grayson?
The transcripts.
What do you mean the transcripts are being degraded?
Exactly what you just said. What do you not understand about it?
So we have transcripts being produced.
Yeah.
Within
extremely low amounts and being.
So you're saying they're being produced at low. Yeah, you're the low level transcription.
Yes, like
of course that's
like such a low level that in actual examples where transcripts
that's what we
do
see
have
in non-coding regions
regions
of the genome.
In actual examples that you can show where a transcript does have a known function, the number of those transcripts is so much greater than the ones you're talking about here that are just like, according to the ENCODE, have some biochemical activity because they have like one transcript. Okay, that transcript just statistically is not going to be able to do anything because it would get degraded so quickly. It would have no effect because its concentration was so exceedingly low.
So low level transcription, especially when it comes to non-coding regions of the genome, that's oftentimes what we see. That's how it functions. It functions and is transcribed differently than in protein coding regions. That's why you have to look to co-expression patterns, epigenetic profiles. See, the thing is, there's only, well, wait, I didn't interrupt you, but you can go once I'm done. There's only so many copies of a transcription factor, basically, that are going to be produced. And so if these transcription factors were merely binding to random sites in the genome, as you say, then there wouldn't be enough transcription factors that are actually available to do the binding that is necessary for these transcription factors to properly function. And so I would argue, here's the last thing I'll say, ENCODE, the ENCODE project, okay, most of the binding discovered in the ENCODE project, I would say, is likely functional binding and not just noise, Grayson.
Okay, so yeah, let's try to stick with one point at a time. When you say transcription factors, that's a different thing than transcripts. When transcripts, we're talking about, mRNA, right? So like when we're talking about transcripts, that's like the RNA, the single-stranded RNA sequence that is the result of these gene areas being transcribed. So when we're talking about everything that you just went through,
right? But Grayson, what are transcription factors binding to?
Yeah, the transcription factors help promote transcriptions at certain areas.
Right, exactly. So if there's transcription, then there's what?
Okay, so I was trying to get to that point because you made multiple points, Donnie. I'm trying to go and address all your points, but if you interrupt me while I'm trying to address all of them with the next thing I haven't gotten a chance to address yet, come on. So what I was going with that was that transcription factors don't just have the equal % chance of binding with every single gene area. That's the assumption inherent with what you just said, that if you don't make that assumption because it's not backed by evidence, then you'd have no reason to think that there are not enough transcription factors and all this falls apart and everything. That is all resting on the assumption that a transcription factor has an equal % chance of binding to anywhere on the cell. Plus, when a transcription factor binds to the quote unquote right area, it sticks there. And there's a difference. Like, that would utterly throw off that math of you saying that there wouldn't be enough transcription factors because you just haven't factored in enough of the actual variables at play here.
So right here from the ENCODE, this is the 2012. I understand there's been subsequent papers, subsequent work. And so they say these data enabled us to assign biochemical functions for 80% of the genome. Transcription, I think, is about 60%, okay, in subsequent studies. And so anytime you say, oh, it's just a handful of these, non-coding regions that are functional, you're not actually addressing the bigger picture, because the bigger picture question is what we're discussing here. Is this 80%, this 80% biochemical activity, is this mostly noise?
So what I'm asking, what I'm telling you,
true function?
What I'm telling you is look at any known transcript that has function, right? If I look at a transcript where we actually know that it has a function and look at the number of transcripts per cell,
right,
and then compare that to some of these that ENCODE is saying have biological function that have like 1 or 3 or 4 transcripts per cell. And then when you look at the ones that actually have known function, you'll see that the number of transcripts per cell is much higher than that when there is an actual known function.
So the problem with that is you're going to find a lot more activity, and the transcription levels are going to be higher, more transcripts produced basically in coding regions of the genome, protein coding regions of the genome.
Not talking about coding regions.
You're talking about what?
I'm talking about in the regions that are specific to these categories, like long non-coding RNA.
Right. You're talking about right. And so once you get into the non-coding regions of the genome, you're going to have low-level transcription. You're going to have some that are higher level. It's very similar.
Quantify that.
It's very similar to your car. Well, it's very similar to your car. Like, for example, my front windshield wipers. I'm using them constantly, even just to, spray water at the front windshield, clean things off. If it's raining, using them. But my rear windshield wiper, I rarely use it, if ever. But it's there, it's functional, but it's functional at a very low level. But it does come in handy when I absolutely need it. And a lot of the non-coding regions of the genome function similar. Okay, where you're going to have a lot of low-level transcription similar to your rear windshield wiper, but it doesn't mean it's not functional, doesn't mean it's not important, doesn't mean it's not useful. Okay,
so my challenge for you is to find an actual a transcript with a known function that has the lowest amount of transcripts per cell that you can possibly find. I want you to find that and then compare that with the ENCODE results. And I think that you'll see something pretty remarkable where the lowest one you can find is still going to have a lot more transcripts per cell than anything that you're talking about with ENCODE that's just like 1 or 2 or 3 or 4 transcripts per cell.
So a functional part of the genome are going to have a lot more transcripts per cell than a part that is just noise, you're saying?
Yeah, to have any appreciable effect, you're going to need to have more transcripts than just, less than a dozen or something.
No, that's completely fine, Grayson. Some parts of the genome are going to function at a higher level than other parts of the genome. Another example is...
Oh, but they're not going to be that low.
Listen, in your car, you probably have in your trunk, a jack and some tools in case you get a flat tire. Now you're going to take those out and you're going to use it to change your tire.
Yeah.
But 99.99% of the time, you're not actually using that jack. You're not using those tools, but you will use them.
But we can see that.
Wait, I'm almost done. When the situation arises,
yes.
Okay? And that's how a lot of the non-coding regions of the genome is. There's a lot of mutational buffer. There's a lot of over-design. There's a lot of redundancy. There's a lot of genes that are basically only expressed under certain conditions, as you love to hear me say. And so, sure, you can show me one with very low activity, few transcripts per cell. That doesn't prove it's non-functional.
So
in the same way, go ahead.
The thing that you're kind of implicitly stating here is that at some point in time, given certain circumstances, then you're having faith that the number of transcripts will markedly increase whenever it needs to fulfill the function that it was designed to fulfill. So unless you can show that, then you're just saying that I have faith that there is a certain circumstance under which that number of transcripts per cell will markedly increase.
That's like saying, Grayson, you've got faith that if you need to use your rear windshield wiper, or you need to use, a jack if you get a flat tire, or the flat tire itself, that's redundant, right? That looks like it's useless sitting at the back of your car. Maybe it's, in the trunk, whatever. You got 4 tires, you get a flat tire. Thank God you got that ready to use. But it's like you're saying, oh, but you just have faith. You got to show me that spare tire is actually useful and functional. No, that's silly. That's ridiculous. The genome comprises so many DNA elements, so many DNA units that are there for those specific circumstances where they're needed. Pseudogenes. We understand that pseudogenes are only expressed under certain conditions. This is just reality. I don't got to prove. I don't got to demonstrate it. It's been demonstrated.
Yeah,
and as time goes on, we're going to demonstrate it more. Go ahead, Grayson.
Yeah, so that's what you're saying, is that we've demonstrated it for 1% of pseudogenes. So you're saying that I believe that not the other 99% will also be able to have some kind of circumstance that we just don't know about yet, under which then their transcripts levels will increase markedly and their real function that was hidden until then will be shown if the right kind of circumstances come about. And just because we have that for 1% of these pseudogenes or these, retrotransposons or whatever, like you're saying that you think that all of them must be like that if we know that 1% of them are.
No, because again, this goes back to your circular reasoning. You're avoiding the bigger issue, because what we're talking about has to do with that 80% biochemical activity. Within that 80% comprises a whole lot more than just 1% of pseudogenes. You have a lot of pseudogenes within there.
Okay, so let me ask you something.
If that 80% is if that 80% is beneficial activity, if it's functional activity, then the pseudogenes that comprise it are also functional.
Okay, let me just ask you something real quick. So do you think that if we just took a random sequence, right? It was determined at random. We just made a random genetic sequence, right? And we inserted it into your genome. And then we did ENCODE's test. And we saw what level of transcription that random sequence that we created randomly to have no function. Are you saying that you think that ENCODE would not detect any amount of transcription, any amount of what they called biochemical activity? You don't think it would detect any amount of it in that random sequence that we insert?
So we make a sequence,
yes,
insert it into the genome of a human being, and then test it to see what activity it has?
Yes.
Well, that's an interesting hypothetical. I don't know. Have they done that before?
So I'm saying that you will be able to detect spurious activity on that segment of just like background amounts of transcription, but it's not going to rise anything major or significant. It's just going to be background. Because
is that your prediction?
Yes.
Okay, but we haven't tested that.
So I'm asking.
It's an interesting prediction.
Would
Well,
your prediction be that there should be no activity?
Well, it depends. I can add a subwoofer to my car and put it in the right spot where it works nicely and the radio sounds good and the music sounds good. I added it in there and connected it in the right spot. So maybe
I'm not saying a subwoofer, right? I'm saying a random sequence.
Right. I'm just saying maybe you can make a random sequence, insert it in the human genome in the right spot, in the right way that allows it to have some kind of functionality. Is that impossible?
So then all of a sudden, what you were previously describing as intelligent design, the same results can be procured with just random design that didn't involve any intelligence.
Yeah, but aren't you intelligently making this sequence?
A random sequence?
Okay, so a random sequence, then you're probably going to be able to detect that it's noise, that it's junk, it's not doing anything.
So then you would predict that it would not be transcribed on any level.
I think so. If I had to give a prediction on that, I have a feeling that'll never be tested. It's unethical on humans, right? To do knockout tests or insert genes and things like that. But that's an interesting prediction. I'd probably say it's not going to have much evidence for functionality, but I'm just curious. What would be your prediction then in terms of max functionality in the human genome? Right.
I think we should look at constrained, like if it's the amount of unconstrained sequences versus constrained sequences. That's a much better proxy for sequence dependent functionality to me.
Well, I guess, okay. If you consider coding regions, non-coding regions, consider it all, right? I'll put a prediction on paper. I'm going to say about 80%, somewhere between 70 to 80%, because I understand mutations happen, damage happens. And so I'm not going to say the genome's 100% functional because the genome has degraded over the course of thousands of years. So I'll say somewhere between 60 and 80%. Okay. I wouldn't be surprised if it was 80%. So what would you say? Non-coding, coding, everything considered.
If I recall correctly, the last study I saw that measured the total percentage of conserved versus non-conserved sequences was something like 10 to 15% are conserved and the rest are unconserved. So, 85 to 90% non-functionally, like non-function based on like the sequence the function does not depend on the sequence.
I'm not that impressed with conserved versus non-conserved because just because a region is not conserved does not mean it's non-functional, because we understand some DNA sequences may be able to tolerate error more than other sequences, or maybe the mutation.
You have to ask why that is, though. Like the reason that they're more robust is because like the actual parts of that gene or that gene area that were necessary for function were not 100% of the total sequence. It was just a small proportion of those like nucleotide, those base pairs that were the truly essential aspects, like the part in the active air, like pocket for the protein or something.
Well, just in general, your non-conserved sequences, right? Mutations in those sequences may have functional consequences that we're not yet aware of. Like I would predict there's much more mutational buffer or DNA utilized for chromosomal stability and integrity than we currently understand.
Perfect. So those are functions that are not necessarily strictly tied to sequence. So then those would be unconstrained, relatively unconstrained areas.
Right.
So if we do see nested hierarchies of similarity between species in those areas, then that would be showing evolution.
So are you basically saying, so for the audience sake, so purifying selection, right? That basically removes mutations or new variants in these constrained sequences, these conserved sequences, and it keeps the genetic sequence the same because, that's where you find DNA units and sequences important in the heart, lungs, keeping us alive, basically, right? And so the regions of the genome that are not under purifying selection or adaptive selection, they're just evolving neutrally over time.
Yes. Yeah.
Okay. But now would you say because they're evolving neutrally over time, they are functional or non-functional?
I would say their function, if they have one, does not depend on their sequence.
Okay, but
they can be
what's
functional.
What's a specific non-constrained sequence in the genome that you think is a problem for us creationists to explain?
The majority of the genome is not constrained.
Right. Okay. But like you're talking specifically about like ERVs or pseudogenes or gene deserts. Like, what are you talking about?
Because within each of those categories, there are constrained and non-constrained regions within both of those.
Well, because
so I'm just talking about the non-constrained regions.
And you're saying because the non-constrained regions, functional or not functional, because they form nested hierarchical patterns within kinds?
Between species in general.
Well, I still don't understand why you believe that's an issue for us.
Because that shouldn't be the case if these were separately created.
Because we find nested hierarchical patterns in functional regions within the genome?
No. In unconstrained regions.
Right, but they're there for functional purposes. So why wouldn't they be found in hierarchical patterns?
Because the function does not depend on their sequence. So we would not expect there to be sequence similarities if they were separately created.
Let me weigh in on that real quick. To me, that's a lot like, the flood would mix everything up in one big alphabet soup mess. That's how bad that argument is to me. You guys typically talk about sequences. You're talking about linear position, but the genome doesn't exist in linear space. It exists in 3D space. So I like to think of the genome. So you got your roughly 2% protein coding region. It's the portion of the genome that is kind of like the factory that produces the material that your body's made out of. And you got the other 98%, a large part of what you guys are calling unconstrained. That's regulatory information that tells the material where to go.
Absolutely not. Absolutely not, T-Rock. The regulatory non-coding sequences are still constrained. They are not unconstrained.
Just hear me out. I'm not saying 100% of the 98 other percent is regulatory. That's not what I'm saying.
But you just said that the regulatory stuff was unconstrained, which is not true.
Oh, well, okay. But no, what I said was the other 98% largely unconstrained.
Okay.
So, and that's essentially what you said a little while ago. You said what did you say?
I would agree with that statement then. I just don't agree with the statement that you can include regulatory regulatory sequences within unconstrained. They're
fair enough, because I know that there's actually a variety, and this not being my field, but what I do know is that there are a variety of mutation rates dependent on the exact type of DNA you're talking about. And I couldn't go over the list, although somebody did share it with me here a while back. There are a number of categories that geneticists slot DNA into. And so you've got your protein coding, you've got your regulatory, you've got RNA, you've got microsatellites. There's so many different categories that it's basically an encyclopedia to go through all of the different things that DNA is related to, right? My main point being that when you say unconstrained regions of the DNA, because there are, how is it that you say it? Because there is a nested hierarchy, it somewhat invalidates the creation idea.
Yeah.
So to me, that's much like the flood makes alphabet soup out of everything argument. It's that bad.
But explain why, though.
Because there's a couple really good functional reasons for that. One of them is that if the genome were so fragile that it had to be in an exact sequence, everything would go extinct very quickly. So there's a lot of redundancy built into it.
Sure.
Another reason
that doesn't invalidate the argument in any way, though.
It does, because hear me out.
Okay.
Hear me out.
No, I understand the point you're trying to make, though, but I don't think you're understanding how that fits with the point I have, because the point you're trying to make is that, like, it makes sense that we should have unconstrained regions, because, like, if every single position of every base pair was necessary for function, then like 1 or 2 mutations would just be catastrophic and things would go extinct like in a couple generations, if not like 1 or 2. I get your point with that, but what I'm saying is that if, like, for functionality, if the sequences in those unconstrained areas can just be whatever, which would be the case if what you're saying, like, it wouldn't matter what the are in those unconstrained regions, like, as long as you have those big unconstrained regions present, then the function that they serve would be independent of whatever sequence they have. So if they do have sequence similarities between different species,
say that part one more time.
Okay.
Would be independent of. Say that part one more time.
Yeah. So in the example you just gave of saying, like, it's good to have portions of the genome that are unconstrained, because then you can have mutations in those portions and they don't have huge effects. So there, you can see a benefit for that. You could see some sort of functionality, but it doesn't matter what the sequences in those unconstrained regions are for it to have that functionality. You follow?
So are you saying, because let's say a function in,
yeah,
I
can get another example.
Well, like, okay, go ahead.
Yeah, so like for certain, like since we were talking about regulatory, or we were talking about enhancers, right? There's a 3-dimensionality to this, just like what T-Rock was saying. So in order for the enhancer to have effect, right, it needs to bend the DNA physically to then like form a little loop so that it can interact with the gene, the promoter region that we're talking about. And so for that loop to be functional, for that enhancer to be functional, you need a certain number of base pairs to form that loop in 3-dimensional space. But it doesn't matter what their sequence is. The actual sequence of the nucleotides in that loop doesn't matter for them to form the function. What matters is the total number of base pairs you have, just so you can make that 3-dimensional loop for you to have that actual 3-dimensional structure for the function to happen. But the sequence of that loop could be anything, as long as it's the correct, like, say 500 base pairs. It doesn't matter what those 500 base pairs are. The important thing is that they're 500 base pairs, so that you can have the proper size of the loop to have this 3-dimensional interaction.
Okay, so this certain interaction or function, are you saying that if it's different in terms of sequence between different species within the same kind?
No, like in the unconstrained regions, we see a nested hierarchy between species.
Okay.
When you say between species, between 2 different species.
Yeah, that you guys say are different created kinds.
Can you? Okay. So
are you saying that they shouldn't be there because basically they're accumulating mutations over 4,500 years, and so the hierarchy shouldn't be there?
They shouldn't be there because there's no functional reason for them to be similar.
Okay, that's where I'm gonna completely disagree with you. When you say there's no functional reason, as I understand it, most of the reference frame there has to do with the knockout gene concept. Is that fair?
No, I would just say you can measure how constrained they are. If they're unconstrained, then we know.
But what standard are you using to say they have no function?
Because again, this is not just no function. I'm saying that you can have function that is not dependent on the sequence. That's the key thing that you're leaving out when you're asking about just function. The important thing is that the function needs to be dependent on the sequence.
No, and that's what I'm saying is exactly wrong.
What are you saying is exactly wrong?
I don't know. I don't understand why the sequence that the function depends on can't be different in between species of the same kind or form a hierarchical pattern.
I'll tell you why I think it's completely wrong, Grayson. It's because when you're talking about protein coding in constrained regions, again, I'm going back to the building analogy. You have to have materials, but you also have to have instructions to put them together. Information does not operate the same way material does. Information can operate outside of 3D space, but material can't.
But again, all of that is still constrained. You're just talking about constrained. We're talking about unconstrained.
I know.
So let's talk about the same thing.
That's what I'm saying is the unconstrained stuff, because a lot of it is information bearing. It's
no. That's the thing. The information bearing stuff is constrained.
100% of it.
If it's constrained, then it's information bearing. It's important for function. If it's unconstrained, then definitionally, it's not going to have any sequence information.
Okay, it's not going to have any sequence relevance, maybe, but it sounds like a circular argument. So when you say information, you probably mean something different than I do.
I'm just talking about if it's conserved versus non-conserved. If it's non-conserved, then the information about its sequence is not relevant for its function.
So let me ask you this.
Yeah, but this also isn't like synonymous mutations versus non-synonymous mutations, right? You have one that's conserved, one that's not conserved, basically, because I mean, I can explain it, but I think you know what I mean. So synonymous mutations basically don't change the amino acid sequence, and so the codons change.
Yeah. So then it's exactly, then it's non-constrained. So then that sequence identity didn't matter. So then we wouldn't expect to see nested hierarchies of similarities between species in it.
We've made predictions on this. Dr. Nathaniel Jensen has like a 50-page paper on this, where these regions of the genome, like third position codon degeneracy, basically have the multi-functions. And so they're there acting as redundant elements, but they also help to slow and speed processes in the cell. And so a lot of these non-conserved regions of the genome, or unconstrained regions of the genome, they form hierarchies within kinds because they have species-specific multi-functions.
And what about between kinds?
So that's where I've been saying all along, between kinds, you have to have a high degree of similarity if you share a food source in common.
But again, not for unconstrained. What you're talking about is just for constrained sequences.
No, Grayson, that's entirely...
Explain that then.
Okay, it goes like this. When you're born, say you're an 8-pound baby.
Let's not start from my birth. Just get to
the Grayson life story time.
Come on, brevity is the soul of wit. Just make your point.
Quit interrupting, and I will make my point. When you're born, you weigh 8 pounds. You start eating and consuming food from your environment. Later, you're a 150-pound individual. Where did all that mass come from? It came from the food in your environment. It's the biochemistry has to be compatible. If it has to be compatible, it has to bear huge amounts of resemblance across similar organisms.
Only in the conserved sequences.
No, absolutely not. Because whenever you consume food, you're doing a number of biochemical processes. Such, for example, you want vitamin C as an antioxidant. You want vitamin A, vitamin D to do antiviral things, and so on and so forth. In order for any one organism, regardless of what species it is, if it can consume that food and get that benefit out of it, even the unconserved regions have to be able to take advantage of it.
No, that's just a claim, though. You don't have evidence to support that.
It's how chemistry works.
No, it's actually not, T-Rock.
So you're saying
I have a degree in biochemistry. That is not how this works.
That's real nice, Grayson. But how are you going to explain if me and a chimp have radically different unconserved regions? How are we going to eat the same food?
It would make absolutely no impact on that.
That is a huge.
No, it's really not, because literally let me explain this here. Every enzyme involved in the metabolism of food is an enzyme, and all the regulatory factors involved, all of that are constrained sequences of DNA. The unrestrained sequences are not involved in that process at all.
Unconstrained sequences are made out of the food from your environment.
You're just saying that your DNA is made from things that you ate.
That's exactly right. Where else would it come from? How do you get your?
What
That
you're
was my
saying is
point.
not logical, T-Rock. You're not
No.
logically tying these points together.
Yes, I am. Your body has to be built out of the things you consume. Period.
We agree on that. I just don't see how that
Okay.
logically follows to try to make your point.
Because if you go out there and eat some molecules of vitamin C, they're going to go into your cell. They're going to do some things to build new cells. Every time your cells divide and reproduce new cells, your old cells have to die out and be excavated from, or they have to be extracted from your system, right? Every single time it happens, you have to go get the same chemistry from the food source and rebuild. That chemistry has things that it can do, and it has things that it can't do. And because
what
it
is
has
your point, T-Rock?
My whole point is this imaginary creation view that you think should be true isn't even realistic, because
no, please just tie what you were just saying to the unconstrained sequences. You are not making that logical tie-in yet. You haven't gone there.
Okay.
You haven't made these ideas relevant to each other.
I kind of did whenever I was saying that information bearing regions there. So in your genome, you've got things that serve structural purpose. You've got things that serve protein building. You've got things that serve a regulatory purpose. You've got things that serve, and regulatory, I guess, could be split out a bunch of different ways, because you've got timing, the exact timing and the chronology of
those are all constrained.
How your body chemistry plays out. But if
those are all constrained sequences.
No, I highly doubt that.
No, but it is
so
true.
You're saying 100% of your regulatory information in your DNA is constrained.
Yeah.
No, that's a myth.
Explain why, or maybe have a source or something, because right now it just seems like you're going based on what your intuition is telling you rather than going based on the evidence.
I mean, that's fair. I will grant that's fair, but the intuition is very straightforward. The reasoning is very straightforward and sound.
Why would I trust your intuition as a lay person on this? I mean, you're not a biologist, you're not a biochemist. Why would I trust your intuition?
So
T-Rock is the jack of all trades. Well, I wanted to ask Grace real quick. So if these unconstrained regions do have multifunctional roles, let's say in acting as redundant elements.
Sorry. Did you say constrained or unconstrained?
Unconstrained. But then, we are at the 5-hour mark, so I might have said
they would be constrained then. If they had multiple functions that were dependent on their sequence, then they would be constrained sequences.
No, because those multiple functions don't necessarily have to be detrimental to the function of the, like for example, your third position.
Are those functions dependent on their sequence at all? If they are, then they are constrained.
Okay, third position codon variation. Is that function dependent on its sequence?
No, because there's a wobble.
Right, exactly. But the point is they have multi-functions. For example, they act as redundant elements, but they also act to slow and speed processes in the cell. There's an excellent paper out that discusses that. And so there you go. We would expect hierarchical patterns in those sequences, in those non-conserved sequences. We also understand there's certain proteins that have multifunctional roles, but those would be constrained. So what do you think? So if they have multifunctional roles and they form hierarchies within kinds and between kinds, would that answer your question?
They would be constrained if they had multifunctional roles. If you just want to talk about the third codon position, like you're not looking at a broad enough scope. We're talking about the scope of like looking genome wide. This is the same problem that you guys had when you were looking at only cytochrome.
Okay, name something else. So name something else. So we got non-synonymous versus synonymous codons, right? What else? That's not constrained.
The majority of all the nucleobases.
But just be specific. Because there's some non.
Like, what do you want me to tell you? Like the 62,528,000 position? Like, what do you want?
Because I can look to any example you bring up, whether it's an unconstrained pseudogene, unconstrained ERV, synonymous versus non-synonymous codons, and I'll give you a multifunctional role for those. And that's why they form nested hierarchies.
Your framework is off on this. We're talking about the total number of unconstrained base pairs. We're not talking about specific regions. I'm not saying like this specific pseudogene is unconstrained, because there's each and every single base pair position has its own amount of constraint to it.
George wants to jump in and ask a question.
There are plenty of positions in the genome that are functional and important, but they don't have to be conserved because they're not integral to the life and development of the organism. And so they can handle a lot of mutational load.
Sure. So then we would not expect to see nested hierarchies of similarity there.
Yes, we would.
Yeah,
Why not?
Yeah, we would.
Because you just said that the sequence.
But they haven't changed that much. They haven't changed that much in 4,500 years. They've accumulated some mutations, sure, but why would they change them to the point where there's no hierarchies?
Because there's literally, like, the mutations could occur anywhere. The fact that the mutations occur in the same places is statistically impossible.
Well, certain parts of your car experience more defects and certain parts of your car are more prone to rust than other parts of your car, and that would happen.
Rust
in all
doesn't have a specific sequence.
Well,
Donnie,
listen,
is George backstage?
Yeah, but you know what? We just hit the 5-hour mark, and I am exhausted.
I think we should let George ask a quick question and then maybe call it.
Okay, because Grayson's nice. This is what we're gonna do. And Grayson, because you and
I feel bad because George has been wanting to ask his question for a while.
Right, and Grayson, you and I, we want to do probably a podcast debate on Lenski's experiment. That's what I thought we were going to discuss tonight. I had a bunch of stuff ready for it, but you know what, Grayson, you and I will chat and we'll book something for Lenski. Okay, you and me, Lenski showdown. What do you say?
All right,
you're going down to Chinatown, George. If you had a couple questions you wanted to wrap it up with.
Yeah,
you sound a lot like me, George.
Huh?
He's joking.
I hear an echo.
Can you hear me now?
Yep.
Yes.
All right. Yeah. Sorry about that. Yeah, it's all good.
Really quick. Can you mute yourself?
George, do you have two screens going simultaneously?
George, the problem is not that we can't hear you. It's that we echo whenever you're not muted. Like, we can hear ourselves talk in an echo.
It's like George has more than one window open playing this feed.
How about now?
That sounds good.
No, it doesn't. Okay.
Now myself again.
George, just whenever you're not speaking, just mute yourself, and it shouldn't be a problem.
Yeah. All right. So Donnie, quick question. What is your position on the age of the Earth again? I don't want to misrepresent you.
About 62. I'm a young Earth creationist, as you probably know. So about 6,200 years.
All right, so basically I'm kind of like defending the Bible, whether it be 6,200 years or I believe physicists now are saying 13 billion years. But so I've watched a lot of your debates and a lot of watch Ken's debates. So Ken always quotes 2 Peter chapter 3 regarding the scoffers, etc. But on that same passage, right, the Bible also says that be not ignorant of the creation, because one day with God can be as if it's 1,000 years.
Right.
So if we do the math, right? So let's say 6,000, just for the sake of this conversation. There's 2,190,000 days in 6,000 years, and if we multiply those, it'll add up to around 13 billion, which is according with what physicists are saying now. So my question is, what are your thoughts on this?
Maybe my brain's not working that good at the 5-hour mark.
Let me respond to this.
I completely followed what you said. T-Rock, you want to answer that?
Let me respond. Yeah, so the passage you're referring to, it actually, what people who use that always fail to do is to recognize that it goes in both directions. He says a day is as 1,000 years, but then he turns around and reverses it and says 1,000 years is as one day. That's point number one. Point number two is that entire passage is referring to a prophecy yet not yet fulfilled at that time. So he's talking about forward in time, not backwards in time. So it's completely out of context to try and take that and make that the context of creation.
Interesting. All right. I just wanted to ask that and see where Donnie stands on that. So,
Donnie, do you agree with that?
like,
George,
the point is whether it goes both ways, like a day being 1,000 or 1,000 being a day, because like, you know, the Bible could have said one day can be 5,000 years, you know, but it's just kind of defending it, like it's according with science, you know, because scientists and physicists have been saying for years that the age of the universe is 20 billion years, but now it's like, oh no, it's 13, and it's
you know,
interesting, like when you do the math, how it just
I'm not all up.
13 billion.
I'm not all up on this specific point. I know Grayson is, and this will open up a can of worms. But from my understanding, the James Webb Telescope has revealed that your most distant galaxies look fully formed. You know, they look like galaxies that are closer to us. And so I was reading, not extensively, but I was reading that they've had to like double the age of the universe just to explain how these early galaxies during the expansion after the Big Bang could be fully formed and essentially look very similar to galaxies that are young. You know, that fits the creation model because, yeah, the galaxies would look fully formed and created. I see Grayson unmuted, but, you know, I find that to be interesting. Have they doubled the age of the universe because of this? You know, if so.
No, absolutely not true.
I personally, I would have to agree with that, because in order for them to technically do that, I think you'd have to see a plethora of quote unquote peer-reviewed papers out before anybody would start endorsing that.
So
I'm not like denying creation. Sorry, Grayson. I'm not like denying creation at all. But I'm just saying, like, why can't it also probably 13 billion to us, right? Not it might be like 6,000 day to day, but maybe it's like that 13 billion to us, but to God it's probably 6,000, etc.
So I want to clarify a point real quick, though, George. Something you said. You said science says the Earth is whatever age, but science doesn't say that. Scientists say that with their opinions. Empirical science, it has always been my position, and I'm in the same boat as Donnie when it comes to the age of the Earth, roughly 6,000 years. It has always been my position that there is no empirical science that can tell you what the age of the Earth is. It can put constraints on it. It can put upper limits and perhaps some lower limits, but definitely upper limits. Empirical science can do that. But it cannot tell you what the actual age of anything is.
Yes, it can.
Oh no, for sure. I didn't say science. I said scientists, and I'm saying a lot of them, like, you know, agree to disagree, and obviously science changes all the time. But the most recent papers that I've read, all of them are agreeing that it's around 13 billion, like physicists, scientists, whatever. And I'm just saying, like, whether that be the case, the Bible can still be true, because again, God, like it says, one day with God can be 1,000 years. And it specifically really says, be not ignorant of this exact point of the creation, because one day can be 1,000, and, you know.
Sure, I understand what you're saying, but the whole reason he's saying be not ignorant is because he's reminding them of future judgment. That's why he's saying don't be ignorant about it. It seems like a slow passage of time to people, but it's still going to happen. It's still a sure thing. And again, he's talking about future context, but the problem with trying to take that context back to Genesis is that the order, the historical order given in Genesis, is exactly backwards to evolution. So it's more than just the timeline.
No, right. I wasn't really talking about evolution. I'm just talking about like the age of the Earth and stuff.
Right, but it's more than just the timeline or evolution. It's the creation order is just completely different.
Well, gentlemen, I got to say this has been a fantastic night. You know, each open mic is unique in its own way. And so we've had a lot of great discussion over the last few months of open mics. Tonight we got into some heavy genetics and population genetics. It was good to have Dr. Dan here to discuss these. Always good to have Grayson as well. So the more evolutionists, the better. You know, that's what these open mics are about. Get the skeptics in here, get the non-skeptics, different views, and let's hash it out for 5 hours. So